Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on September 21st, 2025, about 6 days ago. And this paper lands a surprising punch. The main result shows that simple mirrors can passively spoof LiDAR, fabricating or erasing objects, and even driving detectors to label phantoms as vehicles with 65 to 74% confidence. The paper is titled, "Seeing is Deceiving, Mirror-Based LiDAR Spoofing for Autonomous Vehicle Deception." And as we will see later, the real-world consequences are striking. Beyond the headline, the work formalizes mirror geometry, validates attacks outdoors, injects them into carless simulation, disrupts full autonomous stacks like Autoware, and surveys defenses whose practicality remains limited. The previous segment set the stakes around passive spoofing. Table I maps a landscape, and it shows that the mirror approach is both mirror-based and passive, supports object addition and object removal, includes geometric modeling, and runs in Carlo with outdoor on-vehicle tests and Autoware stack evaluation. Most prior entries miss the mirror-based column, skip object removal, or lack end-to-end validation, which signals a clear capability gap. Alright, the previous figure mapped capabilities. Figure 2 shows why mirrors matter at the physics level. The left panel depicts data omission, where a specular bounce steers the beam away, so no return lands on the sensor and a blind spot appears. The right panel illustrates data fabrication, in which a mirror redirects light to a secondary object and back, so the system assumes a direct path and places a phantom point at the mirrored location. So while Figure 2 showed the attack outcomes, Figure 1 explains the reflection behaviors that make them possible. Figure 1 presents two panels that contrast diffuse and specular reflection. The left panel shows diffuse reflection, where a rough surface scatters many weak returns across wide angles, so the sensor still receives energy. The right panel shows specular reflection, where a smooth mirror sends a single coherent ray with exit angle theta r equal to incidence theta I, which redirects energy and enables deception. So while Figure 1 contrasted diffuse and specular behavior, Figure 3 illustrates two real attack scenarios. The left side depicts object removal, where a roadside mirror redirects beams away from a traffic cone that marks road damage, so the system infers a clear lane. The right side shows object addition, where a mirror bounces pulses to the vehicle body and back, which yields a phantom car detection with high confidence. These setups are simple and street plausible. So while Figure 3 illustrated street setups, Figure 5 shows real point clouds from an object removal attack at 0 degrees. The full figure contrasts a baseline scan and the mirror case. The left panel shows the baseline cluster from the traffic cone about 4 meters ahead, which appears as a compact, dense return. The right panel shows that with the mirror inserted, the cluster disappears entirely, so the scene looks like a clear lane. This validates that passive redirection can erase a mid-sized obstacle. So while Figure 5 validated object removal, Figure 6 demonstrates object addition with mirror arrays. The full figure shows 3-point cloud panels that increase in mirror count, which lets us compare how surface area drives phantom density. The left panel with 2 mirrors presents a small, sparse cluster behind the mirror. The middle panel with 4 mirrors yields a clearer vertical slab. The right panel with 6 mirrors produces a dense, vehicle-sized cluster that looks convincing, so a detector would likely treat it as a real obstacle. So while Figure 6 produced convincing phantoms, Figure 10 reports system-level consequences. The left plot shows rapid braking by the main vehicle once the mirror attack activates, while the follower keeps speed and reacts late. The middle plot tracks separation distance, which falls below the safe threshold and reaches 0. The right plot shows time to collision plunging below the safe zone and hitting 0, confirming a rear-end crash triggered by the spoofed obstacle. Alright, 2 takeaways stand out. Simple mirrors can passively add or erase objects in LiDAR, and the end-to-end tests show this can trigger hard braking, false detections, and even crashes. The broader implication is clear. Autonomous stacks need mirror-aware sensing, cross-sensor checks, and stronger validation pipelines. That is it for the AI Research Roundup. I am Alex. Thanks for listening.